So the last topic for the day is intersecting planes. If we have two different planes inside three-dimensional space, they might be the same or they might not intersect at all, but most of the time they have an intersection, which is a line. And what we'd like to do is we'd like to be able to convert that back and figure out what that line is. Now, one way to think about this is that each of these planes comes with an equation, and so this is like saying, okay, if I have two equations that are linear, they usually give me a line of intersection, and I want to figure out how to find out what that line is, how to convert that descriptive thing in terms of a pair of equations into a parameterization, like we have been talking about converting in other contexts. So there are a lot of different methods to do this, but the simplest one in some ways is using linear algebra. We have two equations, and what we want to do is we want to figure out how to use one variable to solve for the other two. And the method is one that's going to show up in solving systems of equations, and if you ever take a linear algebra course, you'll see this over and over and over again. The idea is, first step is we subtract a multiple of one equation from the other, and that's going to allow us to reduce the number of variables in the second equation so that it only involves two variables. And then what we're going to do is we're going to take those and we're going to plug them back into the original. We'll describe all the points on the line in terms of one of the three coordinates. So this is a little bit to describe using words. What you really have to do is you have to see it in action to some degree. So let's say we have two planes like x plus y plus z is equal to 0. That's one plane. And the second plane could be x plus 2y plus 3z plus 4 is equal to 0, like so. So those are two plane equations, and they're going to have an intersection, which is a line. So what we want to do first is we want to take one of these equations and subtract a multiple of the other to get rid of one of these variables. So what I could do is I could just say, okay, let's subtract the first equation away from the second. And that'll leave us with the equation x minus x is 0, 2y minus y is y, 3z minus 2z is equal to 2z, and 4 minus 0 is equal to 4. That reduces us to the equation y plus 2z plus 4 is equal to 0. That's the first step. We found an equation that solves for that just involves two variables. The second thing we want to do is we want to solve. We want to solve for one variable in terms of the other. We can do that by moving stuff over to the other side. So y is equal to minus 2z minus 4. That lets us express one variable as dependent on the other. And then we take all of that and we plug it back in to the first equation. We say that now x plus y plus z is equal to 0. That substitutes it back into the first equation. And now we want to do the same thing. We want to solve for this variable x in terms of our independent variable z. So we move a bunch of stuff over to the other side, and we find that x is equal to z plus 4, if I have gotten the arithmetic right, which is very possibly false. So our equation for our line now looks like x is equal to z plus 4, y is equal to minus 2z minus 4, and z is equal to z. So that describes a way to give a list of all of the points on the line. And just like before, maybe I don't want to be confusing. Maybe I don't want to get confused between my input and output variables. And so I should maybe describe it as t plus 4 minus 2t minus 4 comma t, like that. That's a way to give an equation for a parameterized line. And the same method works for taking two equations and turning it into a parameterized line. So that's A kind of rough way to do it, and it always works. There are ways to make it set out and be really systematic, and those are the province of the process of what's called row reduction, and it works with many variables, but this is the kind of most common usage case that we'll see within this class.